very innovative and very progressive topic. And today he's going to talk about quantum machine learning and optimization. Over to you, Ujjwal. You can take it up from there.
Thanks, Ritu. Hi everyone. My name is Ujjwal. I'm a global cloud solution architect with the partner enterprise architect team in Microsoft Partner Success, based in Singapore. And thanks for joining the session, and thanks Global AI team to basically provide this opportunity. In the next few minutes, as we go along, I'm going to talk about this emerging quantum machine learning topic, especially focus on optimization area, and then how we have seen some of its usage in current applications and the future set of applications. So essentially, I'll be going through some of these scenarios, but let's begin very quick overview of let me take the opportunity to frame the opportunity of the quantum representations for all of us very quickly. This particular image is from Science magazine, where it talks about different quantum hardware and the way we generate qubits using different mechanisms. You could see a good reference in terms of the number of the longevity in which the qubits is available for the quantum compute, the success rate, logic success rate, and so on. What I wanted to talk about in this particular slide is essentially about the potential of quantum. It has truly redefined how we think about computing, right, for our toughest computing challenges, and especially when we talk about the quantum computing. Today I want to take this opportunity to introduce and provide an overview about the optimization and in as well as the new emerging area of machine learning with quantum computing, and how quantum inspired optimizations, and in fact, I work with some of our team members in Azure, and collaborate with the product team and the field team using the Azure Quantum Solver. So how it could help in solving some of the problems and some experimentations which we have done. I'll walk you through those examples as well. And uh, just to give, for people who are new to quantum computing, I wanted to very quickly take a minute or so and talk about, despite all the advantages we have made in computing, and the power of cloud, and there's always this problem remaining about what we won't be able to solve, even with all these computing powers we have, right? Not because of the problems are cannot be solved with the classical scenario directly, but because of the time it takes, that the amplitude and the duration of solving those problems is enormous. And quantum computing is is this thing that a lot of people, technology scientists, are looking at to help us solve these kind of interesting problems, because of its ability to solve problems at an exponentially faster rate, right? Now that's because it's truly different way of computing. Quantum computing is the language of nature. It's how atoms and molecule works. It also is in terms of the capability. For example, we could imagine being able to create compound that takes carbon out of air, or design material that would superconduct at a room temperature. Advancements that could help imitate and mitigate the global warming challenges. So there are many of these scenarios, and quantum is redefining the meaning of computing to address planet scale challenges. Let's move on to a very quick, interesting slide before I jump into optimization scenarios. Because even if we are looking at Moore's law, and even if Moore's law did continue doubling the number of transistors on a chip every 18 months, there's still some problem whose scaling obeys a different law. Some problems will still require longer than lifetime of the universe to solve, even with continuation of Moore's law and all of the world's fastest computers. So the bottom line I wanted to bring here is that the day will come when the fastest computers start to slow down because there won't be enough space to accommodate classical computer transistors required for compute, right? And it might be possible that in a decade, it might be in half a century, right? So we don't really know that yet, but it will happen, and eventually we'll run out of the compute scenario. So this slide, it just gives you a perspective of the amount of, you know, uh, memory which is required to simulate a qubit, and the time to simulate one unitary gate using that kind of compute power. All right, so now I wanted to jump directly into this interesting aspect of optimization, right? And before I do that, I wanted to give you the perspective of, at the simplest, what optimization is. It's essentially just a process of selecting the best thing from a set of possible options, right? We can best define it in many ways, but when I wanted to think about it, I think of it as an option with the lowest cost, the quickest runtime, or maybe the lowest environment impact. To speed things up, we usually just generically refer this particular definition of the best as a cost to be minimized. And we wanted, if we wanted to maximize the cost instead, for example, we wanted to maximize energy output from a solar cell, all we need to do is multiply the cost by -1 and then minimize it. So now, usually, when we say we have an optimization problem, we mean we have a pretty complicated one, right? Where lots of variables can interact in many ways to influence the cost. We call a particular arrangement of variables the configuration of the problem. Because there are so many problems or possible configurations to choose from, it gets really hard for us to identify the best solution, particularly when the problem space is really large. And it can be easy to get stuck in, local optimum, like we see on the graph here, right? Um, the the way we uh, we look at the cost, and the way the cost varies as a function of these different configurations give us what we call the cost function, the line of our graph here, right? So what I wanted to next talk about is continue through this, and wanted to give a quick example of how we could illustrate this in a traffic minimization problem. um, and the aim here is to reduce the congestion in our road system in order to reduce the amount of time spent in sitting in the traffic. And each configuration represents a different combination of routes that we have assigned to each of the car in the simulation. The cost is the overall traffic level, or the congestion level, which is what we want to minimize. Here, we could see, or we see highlighted some examples of different systems configurations, which each have, as a different cost value. So the redder the road segment, the higher the traffic, and therefore the greater the cost here, right? So I, continuing with this, let's move on to the next slide, where I would go ahead and exactly show you, right? So essentially, as you could see here, this particular configuration is incredibly congested, right? The whole red segment, and we assign the same route to many cars in the simulation, and the traffic is building. The cost is therefore relatively high in this case, right? Now, this configuration, on the other hand, is much less congested. We have assigned cars to a more diverse route in order to reduce the number of cars present on any particular road at a time. Now, this configuration, therefore, has a lower cost. So, how do we tackle, this optimization or tough optimization problems then? How do we optimize getting trapped in these local optima and thus find good solutions to our optimization problems? So there are many ways to tackle these problems, ranging from purely classical methods such as tabu search and simulated annealing to quantum inspired methods such as sub-stochastic Monte Carlo and simulated quantum annealing through to purely quantum optimization techniques. Now, as you might guess, these different methods which I'm mentioning here will perform differently depending on the nature of the problem you're trying to solve. And essentially, there is no silver bullet or solution, right, that would fit all problems. With this in mind, we have to build our own quantum optimization service to provide you with a selection of different solvers. The format you use to submit problem to the services remain, and when I'm talking about submit problems, I'm talking about this service from Azure Quantum in Microsoft case, or in general, when you're looking at the problems, you would have to think about the different types of problem and the problem solvers. And in this case, when we are talking about submitting problems to the service to solve that, it remains the same regardless of the type of solver you choose, giving you the flexibility to experiment, tune, and ultimately find the best fit to solve your optimization problems. And this is essentially in case of Azure Quantum as one of the examples. Now, I wanted to take a case study of the traffic optimization, which we did last year with Ford Motor Group, to develop a prototype solver to tackle the problem of congestion within a road network. So in this example, we simulated about 5,000 cars traveling to and from various locations in Seattle at rush hour on a Friday. Now, each car was given 10 minutes or 10 different routes um, and options to choose from. The aim here was to minimize the congestion across the network, but also to minimize the average the commute time of the people driving. So after all, you could easily reduce congestion by sending people on 3 hour scenic tours or detours. But I don't think anybody would be thanking people for that. So on the left hand side, what you could see is starting of the state of simulation of all choosing the fastest route offered to them. As you could see, this map is incredibly congested, with many cars assigned to the same route. Hence, there is this dark red kind of scenario out here. And our optimization started at this point, and within 26 seconds, running unoptimized code, we were able to reduce the overall congestion by 73%. And the average compute time by 8%. Now, this is, of course, tunable and extensible depending on the scenario. So, our other related key areas, I would say that we are currently building solutions for a freight scheduling or logistics scenarios. These are some of the interesting areas, which could come across. And, there is a solution simulation demo, which, I'm just trying to execute in this case, and you could see the steps going on in this scenario. All right, moving on to the next case and scenario, let me talk about the simulation, which I just ran and executed. I wanted to talk about the next step around the machine learning part, which is very interesting. I wanted to, I would say this is traditionally uh, optimization technique as well, but some application of machine learning algorithms in the quantum case. Um, I want to introduce this case study we did with Case Western Reserve University involving MRI, magnetic resonance imaging. When a doctor look at an MRI, they are relying on experience to decide whether the brightness or the color of a particular area indicates that the tissue is diseased or healthy. Now, magnetic resonance fingerprinting is a technique that gives doctors quantitative results across a range of tissues properties. So you can think of it as the difference between putting your hand on someone's head to feel your for temperature, or versus the number of numbers from a temperature reading, right? So that's kind of a difference. And magnetic resonance fingerprinting works on by producing numerical measurements, right, of tissue properties for each and every pixel of an image. So it does this by using very intricate pulse segment that generate distinctive signals for the different types of tissues within a patient's body. Those patterns are then compared to a vast library of tissues with a known magnetic resonance fingerprint that can be calculated directly from physics simulations. And so a pattern match could be used to diagnose the colon or any type of cancer. And in this condition, um, like multiple sclerosis or epilepsy, the fingerprint scans can pick up changes in the brain that are invisible with conventional methods. Now, the trick with magnetic resonance fingerprinting is figuring out which out of the vast array of problems pulse sequence to use, and which sequence will produce scans quickly and with enough accuracy to distinguish between a healthy tissue and a different manifestation of disease. And so we tackled this complex optimization using quantum inspired optimization. The goal, essentially, in this case, is to have faster and more accurate MRI scans, basically to be able to use earlier detection, avoid necessary surgery through better diagnostics, and increase MRI throughput, lowering the cost and discomfort. The hard optimization problem in this case is pulse sequence has thousands of adjustable parameters which interact strongly, and the optimization landscape is exponentially large and non-convex. So this is a very interesting problem and the use case scenario, right? So which we worked through. Essentially, there is this traditional MRI and then the magnetic resonance fingerprinting, which I just talked about in this slide. Let me just walk you through the pulse sequence generation pipeline in general, right? So first we use this quantum inspired optimization to generate the pulse sequences, and then test them using a MRI simulator measurement success using a quality metric and iterate. Now, once we are happy with the simulation results, we apply the generated pulse sequences through volunteer scans, both healthy and with a brain tumor in this case for validation. And once the sequence has been validated, they can be pushed out to clinical practices more widely, for investigation, ongoing investigation, and so on. So this is one of the example where we could see the result. So for the first part, the iteration loop with the simulator from the left hand side of the previous slide, the quantum inspired optimization produced candidate pulse sequences and runs them using the MRI simulator, right, and evaluates them according to success criteria, which is, for example, inner product of gray white materials, matter signals, and the magnetization values. So, which you could see plotted here. Now, optimization for large magnetization ensures like good signal to noise ratio. Small inner product between the gray and the white matter signals ensures good distinguishably of the tissues and high contrast images. And there's also a trade-off between the two, right? Like, don't necessarily know what the best point of on the curve is. Therefore, do parameter sweeps using quantum inspired optimization and generate sequences, then test against a simulator using compute power, which could be in our case in Azure. It could be any other compute power which could leverage. Now, using quantum inspired optimization can also produce portfolios of options rather than just one. Right. So here, the second phase is, of course, testing the pulse sequence using volunteers. And in these test cases, we have observed that the time taken per slice is reduced by 2/3 by using the quantum-inspired optimization generation pulse sequences without compromising in the image quality, which essentially triples the scan speed at no loss of image quality. And this is a huge win for patients, right? Essentially faster processing in this case, and higher speed to scan, right? 300%, or I would say um, uh, three times better. And at the same point of time, we look at the seconds, right? 11 versus 35 seconds in the timing for one slice. So more like 30 or 60 minutes to 10 to 20 minutes, could be huge in this case. So the improvement in is due to generated sequences having shorter gaps between the pulses, and the fewer pulses is total use, but don't compromise in the quality, right? So actually, we can deliver qualitatively and quantitatively, say that quantum inspired optimization generated pulse produce results that are indistinguishable by the trained third eye from the current state of the art, and actually have been quantitatively shown to improve image consistently and reduce errors. So these tests are ongoing though, right? So I won't claim anything in this case. It's ongoing, but it's interesting. And just wanted to show you in that picture, this T1 is essentially longitudinal time of relaxation, and T2 in this case is the transverse relaxation time. All right. So just to give the perspective from algorithm driven insight, right? The quantum inspired optimization generated sequences are very clearly different to the ones generated by human experts, right? This has led to further avenues of study as to why these might be um, which could be, as to why this might be, which could produce um, further insight down the road, right? And when we talk about this TR index, which you're seeing, or TR time, it's essentially the repetition time, and essentially it's the length of the time between corresponding consecutive points on repeating series of pulses and echoes. So it's quite interesting, and there are many other examples where we have gone through. So I talked about traffic optimization. There's pharmaceutical discovery and fast material design as well, which has use of quantum-inspired optimization. Let me very quickly talk about another example on the traffic side, which I've worked, which we worked. When I say we, it's Microsoft team worked with. Toyota and Jizz in this case, and in Japan. And now I wanted to, not sure about you, but to me, it feels like it's been years since lockdown started. So even so, I can still distantly remember the frustration of being stuck at a traffic light where one it turns green and then traffic gets moving. The next turn, um, light turns red and then you're stuck again, right? So if you could optimize the timing of these traffic lights, you would not only lower your level of traffic induced stress, but you would also reduce the emissions by reducing the number of idling vehicles, right? So how does this GJs do this optimization? It's an interesting case study, and essentially, first thing first, what they did was they took the waiting time, and map it with a waiting cost, which enables them to express the problem as a specific or special type of optimization problem known as polynomial unconstrained binomial optimization, or in short form PUBO. So this is a type of problem where a variable can take one of the two values, here the binary, and the goal of the optimizer is to find some combination of variables that minimizes the cost. And in this PUBO, or polynomial unconstrained binomial optimization, each variable can interact with many other variables, like k-location interactions, and which increases the complexity. So this is an NP hard problem, right? Fortunately for us, in our case, we leveraged Azure Quantum and the Azure Quantum QIO, which is Quantum Inspired Optimization Solver, and that are designed specifically to tackle these kind of PUBO problems, which in this case, JIS have been using to a great effect. In fact, working with Toyota, Subo, Shusho rather, JIS used Azure Quantum to achieve up to 20% reduction in waiting time over conventional optimization methods. So again, we see the reduction in waiting time with a great impact, I would say. And as I was mentioned, previously, less time spent in traffic means lower carbon emissions as well. So it's a win-win for all of us. Right. Further industry applications, there are a couple of them, right? I wanted to very quickly mention that there are many other examples and scenarios. Of course, in this case, into some of them with optimization, some of them with machine learning scenarios. So very quickly jumping into machine learning part as well, and then moving further on how or where it could be leveraged. So when we look at the machine learning and the quantum machine learning scenarios, basically the goal I wanted to find new applications of quantum computers to machine learning, devise new methods to learn about the quantum systems, and number three is about understanding the fundamental limits the physics places on learning, right? And I would very quickly change my screen and talk about the different options which we have, from a quantum perspective and machine learning scenario perspective. So essentially, we have been going through this area of machine learning use cases and scenarios, which could be categorized into different scenarios as well, including deep learning and the standard machine learning use case and scenarios. So, just to give a perspective here, when we talk about machine learning, it's essentially the algorithms that can learn from and make predictions on data, right? It's the foundation of multiple multi-billion-dollar companies and products, including, for example, a product like Bing in Microsoft or Google itself or Netflix, Facebook, Amazon, Baidu, and many other organizations, right? So, what is the problem, of artificial intelligence? When we talk about that, let me just quickly walk through some of these use cases and scenarios. and just go through the implementation of some of these problems using quantum compute. So, some of these problems are, I'm just trying to list it down here. Essentially, the standard problems that machine learning is used to solve include classification, clustering, prediction, and feature learning, right? So, the next aspect I wanted to talk about is how can quantum computing help, right, in these kind of problems. So one is about computational speed up existing tasks, and essentially the quadratic improvements to sampling problems. Now, quadratic may not sound very interesting as compared to, I would say, polynomial kind of speed, but still, a huge increment in terms of the standard processing power which we get from the classical compute. And then the exponential improvement for well-conditioned inversion tasks, right? So in this case, what kind of models we are looking? So we basically are looking at new models for data, which are quantum models that are not efficiently simulatable, right? So new insights into the structure of learning problems and efficient training with fewer approximations. And a good example, I would say, is the one which I just talked about in a bit more detail from MRI image, like detecting cancer by the quantum-inspired solvers in using a quantum compute simulation and finding out the cancer markers, right, in an MRI and magnetic resonance fingerprint, basically. So what tools are available today, right? We have different types of scenarios and tools for us to look at. Amplitude amplification. Quantum inference is used to modify underlying probabilities and basically helps us with quadratic speed up using Grover's search algorithm. The adiabatic optimization, and this is exactly what we were been using in many of the use cases examples which you talked about from traffic optimization use cases. Now this is a slowly varying quantum evolution, basically to use to solve energy minimization use cases. And then the linear system algorithms, right? So essentially in this case, we are leveraging Hamiltonian simulation to perform matrix inversion. And I just wanted to, think about the challenges. Essentially, in this case, input problems or input huge quantum database may be needed for typical problems. The output problem is also about reading results. Could be exponentially expensive, and then speed ups essentially in terms of performance advantage relative to heuristics are also hard to prove. It has not been proven, and it's a very relatively newer area, and I've been talking about some of these use cases, but this is a set of slides. In the next few slides, I wanted to talk about the three problems and the if we have known anything around that. So adiabatic optimization, in this case, we have been looking at mapped optimization problem to quantum Hamiltonian. And in this case, in the table below, you could see that we really do not have a clear quantum speedup at present, which was presented by Wecker in his paper around 2013 and 2014. Essentially, there is not much of a input problem. There is not no output problem, but the speedup is generally unknown in this case. Another one is about least squares fitting. So in this case, we are talking about given B and A such, find X such that, AX minus B is minimized. And in this case, we do see, input problems available, as well as we do not see output problem, but we do see speed up, which is exponential. And this was again presented in paper by VB Brown and Lloyd in 2013, and then VB Reuter in 2014. Then there's another method which we have looked upon, which you can think of is clustering and nearest neighbor classification. And in this case, the k-means clustering finds cluster in a large data set. Again, it was presented by VP Kapoor and Swore in 2013, and then Reventros, Mohanty, and Lloyd in 2013. No, there is an input problem. There is not much of an output problem. There is a quadratic speed up, which is not bad, I would say. Then we also look upon the clustering nearest neighbor classification, and in this case, again, it's about k-means clustering finds a cluster in a large data set. Nearest neighbor classifiers classify, based on the closest classified vector. In this case, again, we found input problem is available, output problems we don't see much, and then there is a quadratic speed up, again presented by a couple of papers by Vivek Kapoor and Sware in 2013, and Reventros and Mohanty Lloyd in 2013. Another way to look at it is this quantum Bayesian inference. I'm sorry. In this case, the problem is given a prior distribution PA and evidence B, find the posterior distribution, and here again we have not seen any input or output problem, and we have seen a quadratic speed up. So these are some of the very interesting use cases and scenarios, which are available. And this is the quantum perception model, which is perceptron model. Now this model is to learn a separating hyperplane for a data set. I just wanted to talk a bit more about this quantum perceptron. It is quite interesting, as in the area which it looks upon. And let me try to bring up the slide very quickly out here to speak through this. Essentially, when we look at this quantum perceptron, we are looking at the linear perceptron, essentially one as it's basically a vector v in class 0, which if we have v dot n is greater than 0, and if it is in class 1 if v dot n is less than 0. Now quantum perceptron works by choosing initial guess for angle theta, and let me try to bring that slide. I think I've posted a different slide in this case. Just give me a second to present a slide which I could walk through this very quickly. And then in the interest of time, I will go ahead and present some resources for all of you to actually look upon, which are quite interesting. So in this case, when we look at the quantum perceptron, we are looking at choosing the initial guess for theta, and then taking the quantum state vector psi train as input, and then psi train to theta by psi train. And this state is measured, and then the result is stored. Then the above steps are repeated, and most likely outcome is set to be by the class. And this is repeated for each training vector in the set, and then the classical error is computed, and the weights of theta is updated to optimize the training error. So, I walked through multiple of these scenarios. I walked through, a different set of mechanisms through which we could apply quantum machine learning using quantum computing. Now, what I wanted to do next is essentially go through this particular topic, and basically continue with some of the references for you. But before that, I wanted to very quickly mention that to apply the machine learning models, or build machine learning models using quantum compute, we do have software available from multiple of multinational companies available, and including some of the startups focused on quantum computing. And just to give you a couple of names around who has been working and providing this software kind of inputs for us, I would say that there are multiple of these software offerings coming in from Microsoft to get started. I mean, one of them is through Q Sharp programming language, and we have Quantum Machine Learning Library, which is Q Sharp Machine Learning Library. Then IBM has through Qiskit provides the opportunity for quantum machine learning. Xanadu has this PennyNail, PennyNail.ai, and quantum machine learning. And of course, Google TensorFlow Quantum is one of the other products to look into for quantum machine learning implementation. So, Microsoft, for example, provides this quantum machine learning experience, which you could leverage using Q Sharp code running on Visual Studio Code, absolutely free tool, which you could download and then add Q Sharp uh, resources into it, and including for measurement and compilers and so on, and then access it. Or you could just use the QML quantum machine learning Q Sharp experience using a Jupyter notebook on the cloud, and we have all of that available on GitHub, so you could access it from there. And let me now quickly jump into um, the slide where I talk about the resources before I conclude. I've already gone ahead of time, but I think I would really like you to go through some of these slide decks, interesting links, for you to get started with. If you are interested in Q Sharp and Quantum Development Kit, this is a link to get started. There's also what we have done is we have added on our machine learning and optimization techniques, but not only those optimization techniques. You can actually get started with what is quantum computing and basically get started with Q Sharp using our Learn site. And this is the URL aka.ms learn QC, which is very interesting. Last year, our quantum product team and the research team came together and delivered 5-hour content, which is recorded here. You could go through aka.ms AQDW, and this would provide a 5-hour content from quantum computing and development with Q Sharp and interesting areas of the applications where we have been working with different organizations. Then, of course, quantum katas is very, very interesting, and I also use this for my own learning as well as testing purposes. And this is something which I would highly recommend to leverage quantum katas on github.com/Microsoft/quantum katas. This has like all the way from getting started to implementing quantum machine learning to chemistry libraries, which you could leverage and use for dev and test purpose. And then, of course, there are multiple of these open source libraries, and where I've mentioned about machine learning library as well, which is under the same Microsoft GitHub, and then quantum libraries. And then the Q Sharp community is available for you to join if you have multiple interest in knowing more about what's coming up and not. You have my contact here, so if you have further interest, you're based in Singapore or APAC region, feel free to reach out to me through LinkedIn or Twitter. And thanks again for joining this call. Hope this was interesting for you in the session, and thanks to the global AI team for this session.
Ujjwal, we have a couple of questions.
Sure. Maybe I'll stop presenting and then
I
can
can
we?
read it out. Can read it out. Can quantum
Sure.
computing help power our energy grid?
Sorry, could you please repeat it again?
Can quantum computing help power our energy grid?
Right. Oh, that's a very good question. So, um, uh, when we think about the energy grid, that is an interesting problem, from a machine learning perspective, and there are a lot of research ongoing onto that. Yes, I would say, to give a short answer, yes, this is an area of research. We have been looking into genetic algorithms in the past, from a classical compute perspective, and it's a very interesting problem to definitely look into from a quantum compute perspective. So it's an area of research, I would say, but the potential is definitely there. So I would say yes. And on a side note, I would say that we also have additional advantages on top of it, right? So the advantage is about reducing carbon footprint, and this is something which we are also working on with the energy organizations, especially one of the example in Microsoft case is Dubai Electricity and Water Authority, DEWA, where we have been working to develop new quantum-based solutions to address this energy optimization and other challenges where the classical computers have serious limitations. So to answer the question, yes, there's a lot of opportunity, and there is research going on onto this area.
All right. All right. Usual one question from my side, because as an MVP, I got this PGI invite for Azure Quantum Computing Service, right? But
Yeah.
unlike the IBM one, they have not made it available to everyone to use it and experiment. Okay, so it's not like they have not shared anything. So you have to actually wait in line, request and access, and there's a huge line, so there's months of waiting to get the access. So any idea when why so much mystery around the Azure computing quantum computing service?
That's a great question. So I'm not the best person to answer it, but I can take a guess around it. See, the
Mhm.
essential thing about it is that the service is still in beta. It's not yet generally available, and it's in private beta, or I would say semi private beta. So at this stage, what I know is that we are working with the organizations who are into the quantum state, so we could create case studies and we could work with them to identify the problems and solve before we make it public. So it's like any beta product, right? It goes through multiple phases. If we are
Okay.
in that beta phase, I would say.
All right, all right. Okay. All right. That's interesting, Ujjwal. So we are always, fascinated by quantum computing, and today's session, along with the resources you shared, is really going to be an interesting read for users who want to delve into more details of quantum computing. So thank you so much for making time and joining us, and we look forward to see you on our future forums.
Thank you so much, Priyanka, and looking forward to working together on many of these areas, interesting areas. And just to also mention here that a lot of the contents are available on GitHub, so it's publicly available for everyone to look into.
Right.
And feel free to reach out, to me in case of further questions on this. Thank you.
Absolutely. All right. Thank you, Joe. Thank you so much. Have a good weekend, whatever is remaining of it.
Thanks to you.
Okay. Bye bye. Bye.
Bye.